Good evening, everyone. For this week experiment, which is experiment 6, we will be discussing about torsion of bar. The group members consist of Bavin Raj, anak lelaki Sukumaran, I myself, Muhammad Fazli Fitri bin Shawal, Subaha bin Shawali, and Nur Najiha binti Hanazla. And our lecturer is Dr. Muhammad Arif Sazali, and we are from section SETP 273102.
Hi, Assalamualaikum. My name is Nur Najiha and I will present the abstract of this experiment. Many products and components are subjected to torsional forces during the operation. Products such as biomedical catheter tubing, switches, fasteners, and automotive steering columns are just a few devices subject to such torsional stresses. By testing these products in torsion, manufacturers are able to stimulate real-life service conditions, check product quality, verify designs, and ensure proper manufacturing techniques. The objective of torsion bar experiment are to investigate the relationship between torque and the angle of twist of a circular cross-section specimen and to determine the modulus of rigidity of materials. In this experiment, the aluminium alloy, stirrod, and nylon rod were used as a specimen and clamped in position. For aluminium alloy and nylon, the rotation scale was set twice, which were at 400 mm and 200 mm from the fixed clamp, and the pointer was set to 0. While for stirrod, the rotation scale was set at 400 mm only from the fixed clamp. A load of 40 Newton were added by 5 Newton increments, and the twist of specimen for each increment were recorded. From the result, the graph of the twist specimen were plotted and the modulus of rigidity can be calculated. It shows that the angle of twist is directly proportional to the torque and length of the rod. The angle of twist was also affected by the type of material. Besides, the modulus of rigidity is inversely proportional to the angle of twist. In short, the objective of this experiment is achieved whereby the relationship between the torque and the angle of twist are directly proportional to each other. Meanwhile, the difference between the value of calculated modulus of rigidity and experimental
point in the circle of the shaft. Theta is angle of twist and L is length of shaft. It also follows that the shearing strain is maximum on the surface of the shaft, where rho is equals to C. Therefore, theta is angle of twist, and L is the length of shaft. Consider the case of a shaft of length L and of uniform cross sections of radius C subjected to a torque T at its free end. The angle of twist and the maximum shearing stress are related as gamma maximum is equals to C theta over L. In the elastic range, the yield stress is not exceeded anywhere in this shaft. Hooke's law applies and gamma maximum is equals to torque maximum over G, where gamma maximum is equal to tau maximum over G, which is Tc over Jg. Solving for theta, it shows that theta is equals to TL over Jg, where theta is angle of twist, T is torque exerted on the shaft, L is length of the shaft, J is polar moment of inertia, and that's the formula, and G is modulus of rigidity.
Let's try with this operator. So the operators that we use in this statement are, the first one is torsion bar.
Hi and Assalamualaikum. My name is Bahabin Shauri. So today I'm going to present about methodology and conclusion. For the methodology, the first step is the aluminium alloy rod was clamped in position and the load hanger was placed on the cord. The second step is the rotation scale and a pointer was set at 400 mm from the fixed clamp.
Eight seven zero zero sorry 0.0087. So this is the data for silver. So the silver is the ratio of silver and aluminum is different. So the ratio of silver is 4.9. So we got different as silver. So but it's a different from the one we got only is a word of book of the millimeter. So we got annual load 18 meter, number one. Number two, we got torque 18 millimeter, and the last one we got is a word of book from millimeter only. diameter of nano rod is 6.525 millimeter. So we got the regular load, Newton, cos piece of rod over 400 millimeter and over 200 millimeter. It's same as the same as the aluminum alloy rod. So, for example, we got annual load for nano rod is 3 Newton. So the top is 112.5 Newton millimeter. So the piece of rod for over 400 millimeter, the degree is 8.6 and the radius is 0.1501. And for over 200 millimeter, so the degree is 3.9 and the radius is 0.067. So for the calculation, how we get this out? So when the F is the calculation, so the formula for top is T is equal to F and R. So where the T is out Newton millimeter and the F is force applied Newton and R is the radius of the rod millimeter. So radius of the torsion head. For example, R is equal to 7.5 and 2 millimeter. So we can get 37.5. So 37.5 is diameter. So we need to divide by 2 and we get the radius. So top is T is equal to F times R cos times radius. So for example, we got the cos is 5 times radius is 37.5. So we got 187.5 millimeter. For variance,
which is torque equals to TL divided by JG. Okay, for the part 2, determine the modulus of rigidity of materials. So this is the calculation for the modulus of rigidity. This is for the aluminum alloy rod. And from the graph, the slope is equals to M equals to angle of twist divided by torque. So based on the graph, the gradient of 400 mm in length is equals to 0.0098, while the gradient for 200 is equals to 0.0049. So to calculate the modulus of rigidity of materials, we can use the equation of G equals to L divided by mj, where L is the length of the rod, M is the gradient, J is the polar moment of inertia. Okay, first we need to calculate the value of J. As we don't know, we don't have the information of the J. So from the calculation, J is equals to 155.6386079 millimeter to the power of 4. And the modulus of rigidity is G equals to L divided by MJ. After we insert the value of J, M and L, we got 150 to 5.86 Newton per millimeter square for 400 millimeter. And for 200 millimeter, we got 150 to 5.86 Newton per millimeter square. So the average of G is equals to 150 to 5.86 Newton per millimeter square. Okay, so next is for the steel rod. From the graph, the slope is equals to M equals to angle of twist divided by torque, and the gradient for 400 is equals to 0.0106. So the J that we got here is 60.86982922 millimeter to the power of 4, and hence the modulus of rigidity for 400 millimeter is 35520.16 Newton per millimeter square. And lastly is for the nylon rod. The gradient for 400 millimeter in length is equals to 0.0069, while 200 is equals to 0.00